Welcome to part 4 of our ANSYS Fluent tutorial series on simulating a car engine fire in a ventilated parking garage. If you're following along so far, great job! And if you're new here, make sure to like, subscribe, and hit the notification bell so you won't miss the upcoming parts. In this part, we'll configure the cell zone conditions, which are used to define specific properties inside different parts of the simulation domain, such as volumetric sources of momentum, energy, or mass. In our case, we'll add a y-direction momentum source to represent the jet force of hot combustion gases rising from the fire. In the navigation pane, click on Cell Zone Conditions. From the list of zones, double-click on Fluid_jet. This is the region where we simulate the upward gas jet from the engine fire. Check the box to activate Source Terms. Go to the Source Terms tab, and click Edit for Y momentum. Add one source, select constant, and enter a value of -80 Newton/m superscript 3. Negative sign means the force is acting upward in the fluent y-axis system. Click OK in both panels to apply the changes. Why are we doing this? This step simulates the buoyant momentum caused by the engine fire. Instead of manually modeling combustion physics, we apply a simplified volumetric momentum source to replicate the push of hot gases into the parking garage space, which is critical in fire and smoke movement simulations. In this simulation, the source term is used to represent the momentum generated by hot gases rising due to combustion within the fluid zone, without explicitly modeling the combustion process itself. By adding a constant y momentum source term with a negative value, e.g., -80 newtons per cubic meter, we simulate an upward force that mimics the natural buoyancy effect caused by temperature differences between hot gases and the surrounding air. This approach is useful in cases where the focus is on the airflow behavior, such as smoke movement or ventilation efficiency, rather than the detailed chemical reactions. It simplifies the model, reduces computational cost, and still provides realistic flow behavior that would otherwise result from complex thermal effects. In this step, we are configuring the boundary conditions for the inlet_exhaust zone in our simulation. This boundary represents an opening where air or gases either enter or exit the domain, similar to how gases might be vented in a garage ventilation system. Open the Boundary Conditions section from the navigation pane. Select the inlet_exhaust boundary zone. Set the momentum and turbulence parameters as follows. Velocity magnitude equals -6 meters per second. This value indicates that fluid, likely air, is entering the domain at a speed of 6 meters per second. The negative sign means the direction of flow is into the domain, based on the coordinate system. This simulates, for example, a vent or fan pulling fresh air into the garage to push out the hot, carbon dioxide-rich air. Turbulent intensity equals 5%. Turbulent intensity describes how chaotic or swirly the flow is near this boundary. A value of 5% means the airflow has moderate turbulence, which is realistic for fans or vents where flow is not perfectly smooth. It's a common default value in many practical engineering simulations. Turbulent viscosity ratio equals 5. This value relates to how much the turbulence increases the fluid's resistance to flow, viscosity. A ratio of 5 means the turbulent viscosity is 5 times greater than the molecular viscosity. It reflects a moderate level of turbulent mixing, which improves the accuracy of heat and species transport near the boundary. Why these settings matter? These boundary condition values are essential for defining realistic airflow behavior. The combination of inflow velocity and turbulence characteristics ensures that our model accurately captures the ventilation and mixing inside the garage. For example, if carbon dioxide accumulates due to poor airflow, the simulation must correctly predict how fast fresh air enters and how turbulence helps in dispersing the gases. That's exactly what these settings help us achieve. In this step, we set up the boundary conditions for the pressure-inlet zone. This boundary defines where air enters the domain under a given pressure, typically used when inflow velocity is not known in advance. Here's what we did step by step. 1. Turbulence settings. We applied the following. Turbulent intensity equals 5. Turbulent viscosity ratio equals 5. These values define the level of turbulence in the incoming airflow. A 5% intensity and viscosity ratio of 5 indicate a moderate level of chaotic flow, which is common in practical environments like a garage entrance or open window. 2. Thermal settings. In the Thermal tab, we set total temperature equals 293.15 Kelvin, which is 20 centigrade. This value sets the incoming air temperature. We're assuming that fresh air entering from outside is at room temperature. 3. Radiation settings. Under the Radiation tab, we selected Radiation method equals external black body temperature. Specified external temperature equals 293.15 K. Internal emissivity equals 1. These settings allow Fluent to simulate radiative heat transfer between the environment and the surface. The black body temperature of 293.15 Kelvin defines the surroundings as a perfect emitter/absorber at room temperature. An emissivity of 1 means the surface behaves like a perfect black body, ideal radiator, which is often used for simplified or conservative estimations in thermal simulations. 4. Species settings. In the Species tab, we set oxygen mass fraction equals 0.23. This value defines the composition of the air entering the domain. Normal dry air consists of about 23% oxygen and 77% nitrogen, which we are simulating here. This is important for species transport and carbon dioxide dilution simulations. Final explanation: why these values? The turbulence values simulate a realistic entrance flow that isn't perfectly smooth. The thermal and radiation settings allow the model to account for temperature and heat exchange between surfaces and the environment. The species mass fraction is necessary for capturing the chemical composition of incoming air, especially when tracking gases like oxygen and carbon dioxide. These settings ensure our simulation reflects real-world airflow and thermal behavior at the garage inlet, making the analysis both accurate and physically meaningful. In this step, we're configuring the boundary conditions for the mass-flow-inlet flue_gas zone. This inlet is where the combustion products, mainly water vapor and carbon dioxide, enter the computational domain. We start by selecting mass flow rate as the mass flow specification method, and we assign it a value of 0.1 kilograms per second. This indicates that 0.1 kilograms of gas are flowing into the domain every second through this boundary, which is a crucial input to ensure realistic mass conservation and energy balance in the simulation. The direction specification method is set to normal to boundary, which means the flow enters perpendicularly to the inlet surface. This is commonly used when the flow direction is well known and aligned with the boundary orientation, and it simplifies the setup by avoiding the need to define vector components manually. In the Thermal tab, we input a total temperature of 1200 Kelvin. This value represents the high temperature of the flue gas produced from combustion. Specifying this temperature is essential because Fluent uses it in solving the energy equation to simulate heat transfer, especially when radiation is involved, as it is in our case. Moving on to the Species tab, we activate the Specify Species in Mole Fraction option. This enables us to define the chemical composition of the incoming gas mixture. We set the mole fraction of vapor to 0.65 and carbon dioxide to 0.35. These values are based on typical combustion products from hydrocarbon fuels, where water vapor and carbon dioxide are the dominant species. By specifying these mole fractions, we are effectively defining the burning fraction, that is, the ratio of combustion byproducts entering the domain. This is extremely important for accurate simulation of post-combustion gas behavior, such as temperature distribution, radiation effects, and species transport throughout the domain. These inputs are also critical for simulating participating media radiation, since both vapor and carbon dioxide absorb and emit thermal radiation, which directly affects the thermal profile of the system. Additionally, having this species data allows Fluent to calculate species diffusion and concentration gradients, which can be essential for further combustion or heat exchange modeling. This boundary condition setup reflects a realistic combustion exhaust inlet, and it's a fundamental part of ensuring that the simulation behaves like a real-world scenario. Now we're moving on to setting the boundary conditions for the wall zone. In the Thermal tab, we set the thermal condition to temperature. This option is chosen when we want to directly prescribe a fixed temperature on the wall surface, rather than using heat flux or convection. It simplifies the boundary condition, especially when the wall temperature is known or controlled, such as in cases involving insulated or uniformly heated surfaces. We assign a temperature of 300 K, which represents the ambient or baseline temperature for the concrete wall. Then, we set the material name to concrete. This ensures that Fluent uses the correct thermal properties, like conductivity and specific heat, for the wall during the simulation. Next, we set the internal emissivity to 0.9. This parameter defines how effectively the wall surface emits thermal radiation. A value of 0.9 indicates a surface with high emissivity, typical for rough and non-metallic materials like concrete. High emissivity is crucial when radiation modeling is active, as in our case, because it affects how much heat the wall radiates or absorbs from the environment. We also define the wall thickness as 0.3 meters. This value is needed for shell conduction calculations. We enable the shell conduction option, which is essential when working with thin walls. Shell conduction allows Fluent to simulate heat transfer through the wall, both across and along its surface, without needing to create a full volume mesh inside the wall. This saves computational resources while still capturing accurate thermal behavior for thin structures. Finally, we set the heat generation rate to 0. This parameter is used only if the wall itself is internally generating heat, such as in electronic components, heaters, or exothermic chemical reactions. Since our wall is passive and not a source of internal heat, we leave it at 0. This boundary setup accurately defines the thermal behavior of the wall and ensures proper interaction with radiation, conduction, and the ambient temperature. It's an important step for simulating how the system loses or gains heat through its solid boundaries. After fully configuring the boundary settings for the wall, we can save time and ensure consistency by copying those settings to other similar wall surfaces in the model. To do this, we go to the Boundary Conditions pane and select the Copy option. In the dialog box, we choose Wall as the source boundary zone. This is the zone from which all the settings will be copied. Then, under the To Boundary Zones list, we select Wall_Ceiling and Wall_Floor, which are the other surfaces that share similar thermal and radiation conditions. After selecting the zones, we click Copy, and when the confirmation dialog appears, we click OK to proceed. This action duplicates all the thermal and material properties, including temperature, material type, concrete, emissivity, wall thickness, and shell conduction settings, from the original wall to both the ceiling and floor zones. Using the copy function ensures that all wall-related zones have identical boundary conditions, which is especially useful when those zones are physically similar or expected to behave the same way thermally. It also helps avoid mistakes and speeds up the setup process, particularly in complex simulations with multiple surfaces. Thanks for staying with us until the end of this video. In this part, we successfully completed the boundary conditions setup. From defining inlet flow and temperature settings to specifying species composition, wall properties, and copying settings to similar zones, everything is now configured and ready for accurate simulation. We hope this tutorial was helpful for you. If you enjoyed the content, please like the video and subscribe to the channel so you won't miss the upcoming tutorials. Stay tuned for part 5, we're just getting to the most exciting parts of the simulation process. See you in the next video.